With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello students, let's go on to the next question. What is the value of spin-only magnetic moment of anionic and cationic part of the complex FeH2O6 FeCN6? There are four options which have been given. It's 4.9 bm and 0. The second option says 0 and 4.9 bm. The third option says 2.9 bm and 0. And the fourth option says 0 and 2.9 bm. Now what is bm? Bm is simply Bohr magneton. Yes? Bohr magneton. And what do you mean by Bohr magneton? It is actually the unit for spin-only magnetic moment. Yes? So that is indicated as mu. How do you calculate mu? The spin-only magnetic moment. It is square root n into n plus 2, where n is the number of unpaired electrons in the given species. Yes? Okay. Or other ways you could say in this particular complex over here. Okay. Now we have to calculate mu. Mu for the cationic and the anionic part of this whole complex. Now this complex, even though it has been given that FeCN6 is on the next line, it is actually one whole complex, okay, whose cationic part is FeH2O6 2+. Yes, whereas the anionic part is going to be FeCN6 4-. Okay. Now in this case, FeH2O6 2+, since H2O is a neutral ligand, it carries 0 charge, and hence in that case my Fe would be in its +2 state. Whereas in case of the cyano complex over here, it consists of a -1 charge each. So -6, yes. So if we go to calculate the oxidation state of Fe in that case, let us consider Fe is unknown, and 6 into -1 is equal to total charge on this part of the complex is -4, and hence Fe is going to be what? -4 plus 6, and that becomes again +2. So Fe is in its +2 state, and hence laying down the configuration, we would be writing it as Fe plus 2, whose configuration would be Ar 3d6. Fe has an atomic number of 26, okay, originally, and in that case, Fe, when having all of its electrons without any loss, is going to be indicated as 3d6 4s2. But since it is Fe plus 2, those two electrons have been lost and I'm left with 3d6. Now, whenever I represent it in the orbital form, it's going to be seen in this manner. Just have a look. 1, 2, 3, and 4. So, according to the Hund's rule, we occupy the electrons and then pair them up. Yes, first singly occupying and then pairing. So, these are the 6 electrons. So, as you can see, in the ground state of Fe plus 2, I'm having 4 unpaired electrons. Yes. Now, in each of the complexes part, I mean the cationic and the anionic, we have 2 different types of ligands which are approaching Fe plus 2. In the cationic part, if you go to C, I'm having the approach of H2O ligand. Okay. This is actually a weak field ligand. Okay. So whenever it will approach Fe plus 2, it will never ever enable internal pairing of the unpaired electrons which are present in its ground state. Okay. So basically what it will do is, it will have its 6 pair of electrons occupying the other set of the orbitals just after this 3D one. So I would be having 4s, then 4p. Yes? So accordingly, it will go and accommodate those orbitals. Are you getting my point? So since it's a weak field ligand, no internal pairing of the d electrons is going to take place. Okay. Now, since there is no internal pairing, I'm left with 4 unpaired electrons in this cationic part of the complex. Yes, 4 unpaired electrons. And hence, in that case, what is happening? The calculation for mu for the cationic part is going to be as follows. Root of n into n plus 2. So we substitute this 4 value in place of n, and what we get is as follows. So that's 4 plus 2, and 4 into 6, that makes it root of 24. Root of 25 is, guys, 5. So approximately I would say 24 would be 4.9 bm. Yes, okay. So mu for the cationic complex, which I'm indicating as mu c, is going to be 4.9 bm. Yes. Now what next? Next is the other complex, that is Cn minus. Yes, cyno group. Now when Cn minus approaches the Fe+2 species, it is a very strong field ligand. Okay. Now due to this higher strength, it is going to give me a low spin complex. In short, what would be happening is that there will definitely be internal pairing. Okay. So internal pairing occurs. Okay, what happens? Internal pairing occurs. Means what? Means these orbitals, which in the first case over here, you had seen that there were 2 electrons in the first part and the other ones were 4 unpaired electrons. So these pair up. Yes. And hence what I get is these 3 pairs. Okay, from Fe+2, and then there would be 6 pair of electrons of cyno group accommodating in the other orbitals. Yes, so 2 of D, then 1 of S, and then 3 of P. Yes, so it would be a kind of DsP3 hybridization which would be taking place. Okay, in short, what? I will not be left with any unpaired electrons. In fact, there would be no unpaired electrons. No unpaired electrons. Yes. And hence in that case, if you go to calculate mu for the cyno part, it's going to be root of 0 into 0 plus 2, which makes it of course 0. Yes. Hence in that case, the mu of the anionic complex is going to be 0 bm. Got my point? Yes. So the anionic complex is 0 and the cationic is 4.9. Now let us just see the order in the question. It has been asked as to what would be the anionic and cationic. So anionic would be 0, cationic would be 4.9, and hence in that case, option number 2, which has been given over here, is the correct answer. I hope you understood the explanation. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.